If you slow a fan from 1500 to 1200 RPM, airflow falls by 20%. But pressure does not fall by 20%, and power can fall by almost half. That is the payoff of the fan laws. Let us calculate all three values and show what the equations do and do not predict. Start with one fan, the same impeller diameter, the same air density, and dynamically similar flow. Let the speed ratio, R, equal the new speed divided by the original speed. These conditions matter. The laws are a scaling model, not permission to ignore stall, motor limits, controller limits, compressibility, or a large efficiency change. The first law is linear. Airflow 2 divided by airflow 1 equals the speed ratio. If speed becomes 80%, the corresponding fan curve scales to 80% of the original airflow. The second law is squared. Pressure 2 divided by pressure 1 equals the speed ratio squared. At 80% speed, pressure becomes 0.8 squared, or 64%. The third law is cubed. Air power, and approximately shaft power under similar efficiency, scales with the cube of speed. At 80% speed, the idealized power ratio is 0.8 cubed, or 51.2%. This is why a modest speed reduction can produce a much larger power reduction. Now calculate a real example. At 1500 RPM, suppose the fan delivers 6000 cubic meters per hour at 500 pascals and requires 2.2 kilowatts of shaft power. At 1200 RPM, the speed ratio is 0.8. Predicted airflow is 4800 cubic meters per hour. Predicted pressure is 320 pascals. Predicted shaft power is about 1.13 kilowatts. These numbers define a scaled fan curve, not an automatic installed duty point. The actual airflow is where the new fan curve intersects the system curve. A system with filters and ducts often behaves approximately as pressure proportional to airflow squared, but fixed pressure terms and changing dampers can move the result away from the simple example. Here is a real Longwell duct fan with a speed controller from a product test. The controller changes the operating speed, the affinity laws explain the ideal trend, while verified product curves and measurements confirm the actual result. The cube law also warns against speeding up. A 10% speed increase predicts 10% more airflow, 21% more pressure, and roughly 33% more shaft power. That can overload the motor even when the airflow increase looks small. For geometrically similar fans, diameter scaling is a separate form. At fixed speed, airflow scales with diameter cubed, pressure with diameter squared, and power with diameter to the fifth power. Do not use that form to compare unrelated fan designs. Use the laws to estimate, then verify the complete curve, efficiency, absorbed power, sound, speed limit, motor current, air density, control range, and the real system operating point. Speed review, longwellfans.com